Welcome to the next lecture on wireless communications. Today we will delve deeper into various coding techniques for mobile communications. Let us look at the outline for today's talk. We will begin with the study of BCH codes, followed by the Reed-Solomon codes. We will also talk about the basics of primitive elements and primitive polynomials required to understand the BCH codes and RS codes, as well as talk about minimal polynomials required to construct the generator polynomials for BCH codes and RS codes. So, this is the brief outline for today's talk. Of course, we will start by summarizing what we have learned so far. So, let us recap. In the previous lectures, we have studied the Galois field, followed by an understanding of cyclic codes. What we learnt last time was cyclic codes was a subclass of linear block codes, except that any cyclic rotation of a valid code word forms another valid code word. We then moved into the domain of burst errors, which are very likely in wireless communications. When we get into deep fades, we encounter errors which are not randomly distributed, but occur in bursts, and we also realized that cyclic codes are a very powerful class of error correcting codes which can be used for burst error correction. We finally moved into the introduction of BCH codes, which is a subclass of cyclic codes. Today we will take a brief mathematical detour to develop some tools to understand BCH codes, and then finally come up with a generator polynomial for BCH codes. So, recapping from last time, we realize that the generator polynomial Gx must be a factor of x raised by n minus 1 for a cyclic code. Here this n represents the block length. So, if I have to find out the generator polynomial for a cyclic code of block length 7, all I have to do is take x raised to the power 7 minus 1 and factorize it. All of the factors have the potential to generate a cyclic code. In fact, this is one way to come up with all possible cyclic codes of a block length n. So, we have to note that a cyclic code C may contain polynomials other than the generator polynomial, which also generates C, but the polynomial with the minimum degree is called the generator polynomial. We have also observed last time that the degree of Gx, the generator polynomial, is n minus k. All this is under the assumption that there is a unique one-to-one correspondence between a polynomial and a code word. So, any code word can be represented by a polynomial, and multiplying a polynomial by x merely tantamounts to rotating the code word polynomial by 1 to the right side. Now, let us move over to encoding using the generator polynomial for the case of cyclic codes. A simple encoding rule can be Cx is equal to Ix times Gx, where Ix is the information polynomial. Just like you have the information word, you can represent it using a polynomial. So, Ix is a information polynomial, Gx we know is the generator polynomial, and Cx is nothing but the code word polynomial. Now, please note that Gx has been designed in such a manner that for all possible Ix, the Cx comes out as a valid code word. That is, it has been ensured that the highest power of x does not exceed that of the block length. Now, if you move forward and represent the received word Vx as Cx, the code word, plus Ex, the error polynomial. You can also represent the error by a polynomial. In that case, we can define something called as a syndrome polynomial Sx as the remainder of Vx under the division by Gx. Clearly, if Ex is 0, your Vx will be equal to Cx, which can be exactly divided by Gx, because Cx has been created by a multiplication of Gx with Ix. For any other case, when the error is non-zero, you would get some remainder, and that pertains only to that error pattern, hence the syndrome for that error. Now, we also know that cyclic codes are a subclass of linear block codes. That means it is possible to represent them using matrices, a generator matrix and a parity check matrix. So, suppose you have your g of x represented as g0 plus g1x plus g2x squared, so on and so forth till grx, where r is the degree of gx. Then the generator matrix can be represented as follows. The first row will be g0, g1, so on and so forth until gr, followed by zeros, and then the second row is nothing but a shifted version, and a third row is yet another shifted version, and so on and so forth. Please note that this first row and second row all are shifted with respect to each other by 1, and the number of rows here is n minus r is equal to k. Just like we had a parity check polynomial, we also have a parity check polynomial analogous to the parity check matrix in linear block codes. What is the philosophy? Gx is a factor of x raised by n minus 1, which means that x raised by n minus 1 can be represented as h of x times g of x. So, h of x is the polynomial which will denote as the parity check polynomial. So, since the degree of g of x is n minus k, the degree of h x must be k. Suppose C is a cyclic code in Rn. What is Rn? Rn is capital Fx by Fx, where small fx is nothing but x raised by n minus 1. So, you are doing all the operations modulo x raised by n minus 1. This will ensure that if you multiply a code word by any power of x, it will pertain to a cyclic shift, but the highest power will not exceed that of the block length, so that the highest coefficient moves back into the first place. Hence, we take modulo x raised by n minus 1. Any code word belonging to C can be written as Cx is equal to Ax times Gx. However, Cx into Hx can then be represented as Ax times Gx, which is Cx times h of x, and if you take modulo x raised by n minus 1, you have this as 0. This means h of x has this unique property that if you multiply it with any valid code word polynomial, you end up with the 0 polynomial. It is a very simple yet elegant way to check whether a code word is a valid code word. Let us look at an example. For binary codes of block length n is equal to 7, and that is all I need to specify. Once I said for block length n is equal to 7, find for me the cyclic codes. All I have to do is take x raised to 7 minus 1 and factorize it, which I have done here. There are 3 factors. Clearly, individually all 3 can generate a cyclic code, but product of any 2 will yet still be a factor of x raised to 7 minus 1, and they can themselves generate a cyclic code, and so on and so forth. So, 1, 2, 3, product of these 2, product of these 2, and product of these 2, 6, product of all 3, which is x raised to 7 minus 1, that is the 7th, and unity 8. There are 8 possible cyclic codes, some of them may be trivial. All of them will have a block length n is equal to 7, and we are talking about binary. If you talk about non-binary cases, then the factorization will be different, because the multiplication and addition tables are different in different Galois fields. So, only for binary code, if you designate x cubed plus x plus 1 as our generator polynomial, then based on that we can write the generator matrix, and whatever is remaining, that is, if you have the product of the other two, that will represent your h of x, which is given by x raised to the 4 plus x squared plus x plus 1, and the corresponding H matrix, parity check matrix, is given by the following. We also made an observation that this happens to be the 7,4 Hamming code. So, Hamming code is also a cyclic code. The minimum distance of this code is 1. Sorry, the minimum distance is 3, so it can correct one error. So, it is a single error correcting code. Now, let us continue with our mathematical detour, and let us talk about something called as a primitive element. A primitive element of GFQ is an element such that every field element except the 0 element can be expressed as a power of alpha, alpha being the primitive element. So, example, consider GF5, 5 is prime. So, we know that a Galois field can exist, and also since it is a prime number, modular arithmetic will work. So, let us consider the elements 0, 1, 2, 3 and 4 as the 5 elements of GF5. Then we have 2 raised to the power 0 is 1, but you have to take everything modulo 5. So, it is 1, 2 raised to the power 1 comes out to be 2 if taken modulo 5, 2 squared is 4, 2 cubed is 3. Hence, all the elements of GF5, that is 1, 2, 3, 4, 0, 1, 2, 3, 4, 5 is not an element, 0, 1, 2, 3 and 4 can be represented as powers of 2 here, as you can see, except 0. So, 2 has this magical property of being a primitive element. All powers of 2 taken modulo 5 will jump on the different elements one by one. Therefore, 2 is a primitive element of 5. Primitive elements are not always unique. So, what happens is if you check for 3, you will find it is also a primitive element, but not 1, because any powers of 1 will remain as 1, or 4. 4 cannot also generate all the elements in GF5. So, 2 and 3 can be shown to be primitive elements of GF5. So, you can test that 1, 4 and 0 are not the primitive elements. Now, what is a primitive polynomial? A primitive polynomial, say Px, again defined over a certain GFQ, a Galois field, is a prime polynomial. We know prime polynomial is that which cannot be factorized over GFQ with the property that in the extension field constructed modulo P of x, the field elements represented by x is a primitive element. So, let us go over this definition again. It appears complex. So, let us break it up. So, we are talking about a primitive polynomial P of x. It must have certain properties. First of all, it is irreducible over GFQ. It is also monic. So, it is a prime polynomial over GFQ. Now, we also know that it is possible to create an extension field from a subfield. But what is the property of this primitive polynomial is that in the extension field constructed modulo P of x, the field element represented by x is a primitive element. We will look at an example to illustrate the point. Primitive polynomials of every degree exist over every Galois field. A primitive polynomial can be used to construct an extension field. We will realize this importance because once you are dealing with BCH codes and Reed-Solomon codes, the notion of a subfield and an extension field is important. The philosophy is that if you have GF2, you can construct GF4, GF8 from GF2. If you have GF3, you can construct the other fields like GF9 from here. Let us look at an example. The example is of GF8. So, let us say the primitive polynomial Px is x cubed plus x plus 1, right. This is clearly non-factorizable over GF2, because you can substitute 0 and 1 and check that 1s and 0s are not the x minus 1 and x minus 0s are not the factors. Now, let alpha be the primitive element, and so all the powers of alpha must pertain to elements in GF8, provided they are taken modulo P of x. So, what you do is alpha, let us represent it as z, alpha squared is z squared, alpha cubed taken modulo P of x. So, if you take z cubed and divided by z cubed plus z plus 1, you will be left with z plus 1. So, modulo P x, that is alpha cubed taken modulo P x, will be z plus 1, the remainder. Similarly, alpha 4, so take z raised to power 4, because alpha is represented by z, take it modulo P of x, that is divide by z cubed plus z plus 1, and you will be left with z squared plus z, right, and so on and so forth. So, if you carry down this exercise, you will realize that you have 7 elements except the 0 element, which are the elements of GF8, and it can be verified that all these follow the 8 axioms of a field. Hence, we have just constructed, using a primitive polynomial P of x, the field GF8 from GF2. So, we have this following table. So, let beta 1, beta 2, so on and so forth up to beta q minus 1 denote the non-zero field elements of GFQ. Then what we have is x raised to a q minus 1 minus 1. If you take this one, it can be factorized as x minus beta 1, x minus beta 2, so on and so forth till x minus beta q minus 1. What is the proof? The set of non-zero elements of GFQ is a finite group under the operation of multiplication. Let beta be any non-zero element of the field, then it can be represented as a power of the primitive element alpha. So, what does it mean? We can say that beta is alpha raised to r for some integer r, because alpha is the primitive element. Therefore, beta raised to q minus 1 is alpha raised to r whole raised to q minus 1, you can represent it like that, is equal to 1 raised to r is 1, because alpha raised to q minus 1 is 1. Right? We have seen in the previous example that alpha raised to q is 8 minus 1 will ultimately come down to 1. It will loop through all the elements, and alpha raised to q minus 1 will be 1. Hence, beta is a 0 of q raised to x raised to q minus 1 minus 1, and this is true for any non-zero element beta. Hence, we can write x raised to q minus 1 minus 1 as the product of x minus beta 1, x minus beta 2, so on and so forth till x minus beta q. So, if you consider the GF5, you can close your eyes and simply write as x raised to 4 minus 1, q is 5, so q minus 1 is 4, as x minus 1, x minus 2, x minus 3 and x minus 4. So, now let us go back to our problem, because why are we taking this mathematical detour? We are trying to find easier ways to factorize x raised to n minus 1, and also try to see if we can come up with a constructive technique for coming up with gx with certain desirable properties. What are those desirable properties? The number of errors the code can correct per block, because the strong or weak codes depends on how many errors it can correct, and that depends on the minimum distance of the code. So, what we want to do is, having got some kind of a constructive technique, can we pre-specify how many errors the generator polynomials the code generated by the generator polynomial can correct. So, we know that in order to find the generator polynomials for cyclic codes, and BCH code forms a subclass of cyclic codes, we have to first factorize x raised to the power n minus 1. Now, x raised to the power n minus 1 can be written as a product of p prime factors like this. Any combination of these factors can be multiplied together for a generator polynomial g of x. We had done a previous example where we had taken pains to factorize this and then come up with. The question is, can we directly write this factorization from the mathematical tools we have developed? If the prime factors of x raised to the n minus 1 are distinct, then there are 2 raised to the p minus 2 different non-trivial cyclic codes for block length n. This we have seen earlier. So, let us go over the basic definitions. A block length n of the form n is equal to q raised to the power m minus 1 is called the primitive block length for a code over G of q. This definition is particularly important from the perspective of BCH code. So, a special block length, what is it? It is q raised to the power an integer m minus 1. So, if q is 3 and m is 2, so n can be 3 raised to the power 2 9 minus 1 8. A cyclic code over G of q of primitive block length is called primitive cyclic code. The field G of q raised to the power m is an extension field of G of q. For this, let the primitive block length n be equal to this one. So, we consider the following factorization: x raised to the power n minus 1. This has been our most famous polynomial x raised to the power n minus 1, which has to be factorized in order to get the generator polynomials. Now, n clearly is of the type q raised to the power m minus 1. So, I have substituted here, and this can be represented say as f1x times f2x, so and so forth till fp. This factorization will also be valid over the extension field that we have just generated g of q raised to the power m, because the addition and multiplication tables of the subfield form a part of the tables of the extension field. So, this is an important observation that the subfield tables. So, if you talk about the subfield as g of 2 and extension field as g of 8, then you will see that the addition and multiplication table for g of 8 contain within itself the addition and multiplication tables of g of 2. Since this is valid, then you can write one possible factorization x raised to the power n minus 1 and substituting n for q raised to the power m minus 1 as nothing but the products over j x raised to the power minus bj. So, we have a direct way of factorizing. So, what are minimal polynomials? In order to find the generator polynomials for the cyclic codes of block length n, we have to first factorize x raised to the n minus 1. We have seen it can be written as the product of p polynomials, and any combination can give you a factor. So, the smallest degree polynomial with coefficients in the base field g of q that has a 0 in the extension field g of q raised to the power m is called the minimum polynomial of beta j. So, we are talking about a smallest degree polynomial where the coefficients are in the base field g of q, but that has a 0 in the extension field. It must have a 0 because we intend to factorize it as x minus beta 1, x minus beta 2 and so forth. Let us consider an example. Consider the subfield g of 2 and its extension field g of 8. Here clearly q is equal to 2 and that integer m is equal to 3, hence you have q raised to the power m is 2 raised to the power 3 8. The factorization in the subfield or the extension field yields x raised to the power 7 minus 1. 7 is the primitive block length, is nothing but x minus 1, x cube plus x plus 1, x cube plus x square plus 1. But next consider the elements of the extension field of GF8. These are the following. These elements, if you remember, were just constructed from GF2 using a modulo operation. Modulo operation over a primitive polynomial. Which was the primitive polynomial? X cubed plus x plus 1. Therefore, we can write very conveniently the factorization x raised to the power 7 minus 1 is nothing but x minus 1, x minus z, x minus z minus 1, and so on and so forth till x minus z squared minus z minus 1. That is x minus beta 1, x minus beta 2, x minus beta 3, and so on and so forth. So, what is magical is when you multiply this out, all the terms, all the z terms will cancel out and you will be left simply with x raised to the power 7 minus 1. Now, if this is true, then we already have a very elegant way to pick and choose the factors and also create a cyclic code as strong as we want. Clearly, if we have more number of factors in my g of x, the highest power of g of x increases, that is n minus k increases, because the highest power of the degree of g of x is n minus k. So, if n minus k increases, we are putting in more and more redundancy, right. You can build stronger and stronger codes. Exactly how strong we will just mention. So, if f(x) is the minimal polynomial of beta, then it is also the minimal polynomial of the elements in the set beta, beta raised to the power q, beta raised to the power q squared, and so on and so forth. This can be shown, where r is the smallest integer such that beta raised to the power q raised to the power r minus 1 is beta. It is a property. This set is called the set of conjugates. The elements in the set of conjugates are all zeros of f(x). Hence, the minimal polynomial of beta can simply be written as f(x) is equal to x minus beta raised to the power q, so on and so forth till x minus beta raised to the power q raised to the power r minus 1. Now, we come back to our BCH codes and try to think of a way to create generator polynomials for BCH codes. Again, it is a cyclic code. We have to have a factorization of x raised to the power n minus 1, but this time we will put a constraint on n. It cannot be any arbitrary block length, it has to be a primitive block length. So, what we do is we can write gx as a generator polynomial is simply the LCM, the least common multiple of f1x, f2x, so on and so forth till fpx, where f1x, f2x, and so on and so forth till fpx are the minimal polynomials of the zeros of g of x. We have established this. So, each minimal polynomial corresponds to 0 of gx in an extension field. So, we can design good codes, that is determine the generator polynomials with the desirable zeros using this approach. So, with the primitive block length n is equal to q raised to the power m minus 1, choose a prime polynomial of degree m and construct g f q raised to the power m. So, let us now look at the recipe for getting the generator polynomial for any BCH code. So, start with a primitive block length, right, because the factorization that we have talked about holds good only for these special block lengths. Choose a prime polynomial of degree m and construct g f q raised to the power m. So, keep in the back of your mind that we are constructing, for example, g f 8 from g f 2, where q is 2 and m is equal to 3. Find f I x, the minimal polynomial of a alpha raised to the power j for I is equal to 1, 2, 3, 4 up to p. The generator polynomial for the t error correcting code is then simply given by LCM f1x times f2x up to f2tx. Codes designed in this manner can correct at least t errors. That is, we have a recipe for coming up with a generator polynomial that give us a cyclic code, which is BCH, which can correct at least t errors. You can come up with a generator polynomial which can overdo the design, it can correct more than t errors, but it will guarantee you that it will correct at least t errors. For this reason, d is equal to 2t plus 1 is also called the design distance of the code, and the minimum distance d star could be less than this one. So, you can over design your code using this technique. Let us look at an example. So, we have to start with a primitive polynomial. Let us say our primitive polynomial is z raised to power 4 plus z plus 1 over gf2. Quickly check that it is a prime polynomial, because you cannot factorize it and it is monic. We shall use it to construct the extension field gf16 this time. Clearly, I can construct with an appropriate choice of a primitive polynomial any extension field. So, gf2 is the base field and gf16 is the extension field. Let alpha be equal to z be the primitive element. Then you take powers of alpha and keep on taking modulo pz. So, alpha is equal to z, alpha squared is equal to z squared, alpha cubed is equal to z cubed, but the moment you have alpha 4 is equal to z 4, what you do is take modulo this one. So, you will get z plus 1, again alpha 5 is z squared plus z, and so on and so forth. Again please note, alpha raised to power q minus 1 alpha 15 will give you 1. On the right hand side of the table, we have the corresponding minimal polynomials. Okay. So, what is interesting to note is that minimal polynomials are not unique. So, you have an x4 plus x plus 1 here, then again you have x4 plus x plus 1 for alpha squared, and then for alpha 4 again you have the same thing, and magically for alpha 8, alpha raised to power 8 again you have this, right. Consider alpha cube. You have this term which has all the powers of x raised to power 4 plus x cubed plus x squared plus x plus 1, but it occurs for alpha cubed, again it occurs for alpha raised to power 6, then again it occurs for alpha raised to power 9, and again it occurs for alpha raised to power 12, right. So, there is a definite pattern, the pattern we observed last time, beta, beta squared, and so on and so forth. So, now let us look at an example of constructing the generator polynomial for a particular BCH code. Here let us start with a block length n is equal to 15, and we wish to construct a single error correcting code, that is t is equal to 1. Then the generator polynomial for the BCH code can be written as gx is equal to LCM of f1x, f2x, so on and so forth till f2tx, but t is equal to 1, so we stop at f2. Clearly, it is LCM for f1x and f2x, but from the previous example what we have seen is f1x and f2x are identical. So, this LCM comes to our rescue and we just retain one of them, x raised to power 4 plus x plus 1. Simple. This is our generator polynomial. We have just found the generator polynomial of a single error correcting code. Now, please observe the following. The degree of g of x is n minus k, but here n minus k is 4, which gives k is equal to 11. Why? N is equal to 15, the starting point. Thus, we have obtained the generator polynomial for the BCH 15, 11 single error correcting code. The design distance of this code is 2t plus 1 is equal to 3. it can be also calculated the minimum distance of this code also happens to be 3. If the minimum distance is 3, it is definitely a single error correcting code. In this case, the design distance is actually equal to the minimum distance of the code. Let us now become more ambitious and say, no, we are not happy with t is equal to 1, but I want a double error correcting code. It should be able to correct 2 random errors within the block length n is equal to 15. To do so, we carry out the same exercise, but this time Gx is LCM f1x, f2x, f3x and f4x. Again we take the primitive polynomials like this, take the LCM, and after the product we find x raised to the power 8 plus x raised to the power 7 plus x raised to the power 6 plus x raised to the power 4 plus 1 as the Gx. Again the degree Gx n minus k is equal to 8 in this case, which gives us k is equal to 7 because n is equal to 15. This means we have been able to design a 50,7 code. The design distance of this code is 5, and it can be also seen that the minimum distance is also 5. However, if you keep on proceeding beyond t is equal to 4, you will see that the design distance exceeds the minimum distance. That is, you will start over designing your code. Now, the other part of any good coding scheme is how efficient you can make the decoder. Fortunately, very fast algorithms exist for decoding BCH codes. It should be remembered that since BCH codes are a subclass of cyclic codes, which are a subclass of linear block codes, any of the previous decoding techniques will work. But we have better, more efficient algorithms that have been designed specifically for the BCH codes, looking at the structures. An important method is the Gorenstein-Zeilier algorithm, which is the generalized form of the binary decoding algorithm, which was first proposed by Peterson. Now, let us go into a subclass of BCH codes called the Reed-Solomon codes, or the famous RS codes. RS codes are an important subset of the BCH codes with a wide range of applications in digital communications as well as in data storage. The typical application areas of RS codes are storage devices including tapes, your music CDs, DVDs, barcodes, wireless and mobile communications including cell phones and microwave links, satellite communications, digital TV, high speed modems. Let us talk more about the Reed-Solomon codes. The payoff is a coding system based on groups of bits such as bytes rather than the individual zeros and ones. Here we are actually looking at non-binary codes. So, if we are now talking about symbols and each symbol represents a set of bits, then if we can even make a single symbol error correcting code, then eventually you can correct all the burst errors embedded therein, because correcting one symbol amounts to correcting all the errors within that symbol, but one symbol represents several bits in succession. So, we have actually come up with a very strong burst error correcting code naturally. This feature makes the Reed-Solomon codes particularly good at dealing with burst errors. 6 consecutive bit errors, for example, can affect at most 2 bytes. Thus, even a double error correcting version of a Reed-Solomon code can provide a comfortable safety margin. That is the inherent advantage. The disadvantage, of course, is you have to work in higher Galois fields. The current implementation of RS codes in CD technology are able to cope up with error burst as long as 4000 consecutive bits. So, in this subclass of BCH codes, the symbol field GFQ and the error locator field GFQS by m are one and the same. That is, we are dealing with m is equal to 1. So, the base field and the extension field that we are talking about for so long are one and the same. But in order to make this thing effective, I should start with a large value of q. So, let us put n is equal to q s by m minus 1 is nothing but q minus 1 here. The minimal polynomials of any element beta in the same field q, GFQ, is given by f beta x is equal to x minus beta. Since the symbol field, which is the subfield, and the error locator field, which is the extension field, are one and the same, all the minimal polynomials are linear. Hence, the generator polynomial for a t error correcting code in this case can be simply written as this, which is true for BCH codes. You go from F1, F2 up to F2T. But here again we have a very simple linear product, x minus alpha squared, so on and so forth till x minus alpha raised to 2t. A really very simple generator polynomial for Reed-Solomon codes. Hence, the degree of the generator polynomial will always be 2 raised per t. Okay. So, you can always comment upon the degree of the generator polynomial. Hence, n minus k is 2t. Why? Because the degree of g of x is n minus k. Let us look at an example. Consider the double error correcting Reed-Solomon code of block length 15 over GF16. Please note m is 1, right. So, q is 15. So, q minus 1 is 15. As we have seen in the previous case, n is equal to q raised by m minus 1, q is 16, q minus 1 is 15. So, your block length is 15 that we are talking about. Now, we use here the elements of the extension field GF16 constructed from GF2 using the primitive polynomial z raised to 4 plus z plus 1. We have done this just before. So, the generator polynomial can be written as x minus alpha squared, x minus alpha cubed, x minus alpha 4. Why? Because t is equal to 2. So, the maximum power of alpha is 2t is equal to 4. As simple as this. We immediately have the generator polynomial. We have to expand it out and get our standard polynomial. So, if you multiply it out, you get this, and if you solve this and try to write it in this form, you get this one. Please note, we are working in GF16. We have all the elements alpha 1, alpha squared, alpha cubed, and so on and so forth. So, you have these representations. My generator polynomial will have coefficients taken from GF16, because that is the field I am working on. But please note, by definition Gx must be monic. So, the coefficients of the highest power of x is unity, and rest of the coefficients are drawn from GF16, because these are the elements of each power of alpha is some element of GF16, since alpha is a primitive element of GF16. Here n minus k is 4, highest power, which implies k is equal to 11. Why? Because n is equal to 15. Thus, we have obtained the generator polynomial of a RS 15, 11 code over GF16. Okay. So, clearly, this is a non-binary code. Note that the coding procedure takes 11 symbols, not bits. So, it is 15, 11, but it is not dealing with bits, it is dealing with symbols. But we are over GF16, so each symbol is 4 bits. So, it takes in 44 bits and throws out 15 symbols, which is equivalent to 60. Some properties of RS code. A Reed-Solomon code is a maximum distance separable code, and its minimum distance is n minus k plus 1. Why? Let the designated distance which is designed for RS code be d is equal to 2t plus 1, then the minimum distance d star satisfied the condition d star which is greater than or equal to 2t plus 1. We know this from basic linear block code theory, but for Reed-Solomon code we have just seen using the power of g of x, the degree of g of x, n minus k is equal to 2t, right. Hence, d star greater than d is equal to 2t is replaced by n minus k, but by singleton bound for any linear code d star must be less than or equal to n minus k. Using these two, upper bound and lower bound, we have been able to say that d star is exactly equal to n minus k plus 1 for any Reed-Solomon code. Fine. This table shows some standard Reed-Solomon code parameters. Please note here we have this m, on the second column we have q which is 2 raised per m, and here is the block length. Again this column represents the number of errors that code can correct, and here is the k and the d star minimum distance. Finally, the measure of the efficiency of the code which is k over n, which is the code rate. So, pick for example m is equal to 4 and we are talking about q is equal to 16, for n is equal to 15. If you just talk about a single error correcting code, you have a fairly high code rate. We know that the code rate is less than 1, but if you go much closer to 1, you get a more efficient code. At the same time, if you move down the table and if you are at m is equal to 8, that is you are working at 256, gf q is equal to gf 256 and your block length is 255, then you can have t is equal to 5 error correcting code, but the code rate being very close to 1, 0.96. So, you have a 5 error correcting code, and please note this is the symbol, the 5 symbols can be corrected. So, RS codes form a very efficient yet powerful class of cyclic codes. This is the power of Reed-Solomon codes. Let us now summarize today's lecture. We started off with a mathematical detour and we talked about the primitive element and the primitive polynomial. Then we discussed the definition and the implications of minimal polynomial. We then discussed BCH codes, how to construct BCH codes, followed by the famous Reed-Solomon codes. We will conclude our lecture here, and in the subsequent lectures we will talk about codes with memory, that is convolutional codes. Thank you.